Look at this field of points. Each dot can stand for something real. A customer making a decision, a patient arriving at a hospital, a car seeing a road, a sensor reporting a value, or a factory part moving through a process. This is the world we are trying to understand. It is wide, messy, and full of variation. But when we train a model, we never get the whole world. A small part of what happened is to be measured, stored, labeled, cleaned, and made available. That small piece becomes the training dataset. This is the first idea. A dataset is not reality. It is evidence from reality. Sometimes that evidence is rich, narrow, enormous, and still misses the most important cases. So before we ask how clever the model is, we have to ask a deeper question. What part of the world did our data actually capture? That is why this chapter is called Population versus Sample, the foundation of ML data. In statistics and machine learning, the population is not just a group of people, it means the full collection of cases we care about. If we are building a recommendation system, the population might be all future customers and all the products they might encounter. If we are building a medical model, it might be all patients who could arrive with a certain condition. For a self-driving car, it might be every road, light level, weather condition, and driver behavior the car will face after deployment. The population is the target of understanding. And notice something important. The population is often larger than what we can observe. Some cases are rare, some have not happened yet, some are expensive to measure, some are hidden because the system never recorded them, so the population extends beyond the screen. That is not a design detail, that is the statistical problem. A sample is the part we actually observe. Imagine the population as this jar of colored balls. The different colors represent different subgroups, conditions, environments, or behaviors. A good sample should give us a useful glimpse of that mixture. But the scoop is small. It might miss rare colors. It might overselect one region of the jar. It might collect what was easiest to reach instead of what was most important. Once the sample becomes a table, it starts to look official. Rows and columns can feel objective. But the table still came from a scoop. This is why the notation matters. Sample is a subset of population. The model sees the sample, learns patterns from the sample, and then makes predictions about cases beyond the sample. That jump from sample to population is where generalization lives. Behind every data set is a hidden data generating process. Data does not appear magically as a spreadsheet. It is produced by the real world. Environment matters, human behavior matters, time matters, sensors matter, randomness matters. A camera image is shaped by weather, lens quality, lighting, and the scene in front of it. A transaction record is shaped by customer intent, fraud attempts, business rules, and logging systems. A medical record is shaped by biology, access to care, clinician decisions, and what the hospital software stores. The machine here is a metaphor for that process. Reality produces many outputs: images, transactions, medical records, sensor signals. But only some outputs fall into the dataset box. Some are dropped, some are delayed, some are distorted, some are never measured. So when we look at data, we should also ask, what process created it and what did that process leave out? Now compare two samples. On the left, the sample has roughly the same mixture as the population. Red, blue, yellow, and green all appear in similar proportions. This does not make the model perfect, but it gives the model a fairer view of the world. On the right, the population is still diverse, but the sample is dominated by one color. The model can learn a boundary that looks good inside the sample and still fails outside it. This is one of the most important practical lessons in machine learning. Large dataset does not mean good dataset. A billion examples can still be biased if they come from one platform, one city, one device type, one income group, one language, one time period, or one behavior pattern. More data reduces random noise, but it does not automatically remove bias. Here is a concrete example. A self-driving car model trained mostly on clean, sunny, daytime roads. Inside the training world, the model may look confident. The lanes are visible, the road is dry, the sky is clear. Many examples share the same geometry and lighting, but deployment is not obligated to look like training. The same road can appear in rain, fog, darkness, snow, or glare. The geometry may be familiar, but the input distribution has changed. The pixels the model receives are not drawn from the same conditions it practiced on. This is why test accuracy alone can be misleading if the test set is too similar to training. A model does not just learn road structure, it also learns the world it was shown. If that world is narrow, the model's confidence can collapse when reality changes. Training, validation, and test sets are useful tools, but they are often misunderstood. The training set is used to fit the model. The validation set is used while making choices. Which model, which features, which hyperparameters, which threshold. The test set is supposed to be held back until the end, so it can estimate final performance on unseen data. This split helps protect us from fooling ourselves. But there is a catch. All three sets can be cleanly separated and still be unrepresentative. If the original data set came from the wrong slice of reality, then training, validation, and test are just three pieces of the same wrong slice. So the warning belongs above all of them. All must represent the future use case. Many statistics and machine learning methods become easier to reason about under the IID assumption. IID means independent and identically distributed. Independent means one example does not directly determine the next. If we sample customers at random, one customer should not simply be a duplicate of the previous one. But real data can violate this. Video frames are a classic example. Frame at time t and frame at time t plus 1 are usually almost the same. Treating them as totally independent examples exaggerates how much information we really have. Identically distributed means training, validation, test, and future deployment data all come from the same underlying distribution. If the bell curves match, our evaluation has a chance to tell us something about the future. If one curve shifts, stretches, or changes shape, then yesterday's performance may not describe tomorrow's performance. Distribution shift is what happens when the world moves. The training data may come from 2023, but the model is used in 2024, 2025, or 2026. During that time, fraud patterns change. Customers discover new habits. Devices are upgraded. Sensors drift. Weather patterns change. Competitors appear. Policies change. A product becomes popular with a different group of users. The model can stay fixed while the world around it changes. In notation, the training distribution is no longer the real-world distribution. The probability of seeing certain inputs has changed. This does not mean every model instantly fails. Some patterns are stable, some features are robust, but distribution shift is why monitoring matters after deployment. A deployed model is not a finished statue. It is part of a living system. We need to watch the data coming in, compare it with the data used for training, and ask whether the model is still seeing the world it was built for. So, we return to the opening metaphor. The world is an ocean of cases. The dataset is a bucket of water taken from that ocean. The model learns from the bucket, then sends predictions back into the ocean. At first, the tempting question is, how much data do we have? That question matters. Small samples can be noisy. Rare events need enough observations. More data can help a model learn patterns more reliably. But the better question is, does our data represent the world? A small but carefully sampled dataset can sometimes teach more than a huge biased dataset. A large dataset from the wrong conditions can create a model that feels precise but generalizes poorly. Generalization is not magic. It is a relationship between the sample, the population, the data generating process, and the future use case. That is why the final equation is an inequality. Model generalization is limited by the quality of the training sample. Better sampling does not guarantee a perfect model. But poor sampling places a ceiling on what the model can honestly learn. So when you see a dataset, ask what world it came from, ask what world it misses, ask whether tomorrow's cases look like yesterday's records. In the next chapter, we will go one level deeper into mean, median, variance, and standard deviation for ML. Those ideas will help us describe the center, spread, and stability of the data we collect. Thank you for watching. Stay curious, follow the math, follow the data,